Today's lesson is going to be a review of Chapter 6, and there's not really any new material, but hopefully I'm able to fill in some of the gaps of things that you might not have learned from the previous lessons. A couple of things to point out is all the questions that I'm going to ask you today are actually taken from the self-test in your solutions manual, that I hope that you've found those self-tests and that you're utilizing them because they can be pretty helpful. The answers to those self-tests, all of the questions I'm going to show you today, are also in the solutions manual, and so if you would rather, you can just work on these problems on your own and then check your answers and then come back to the video to see if you need any help with the questions that I'm going to go over right now. Additionally, I've also kind of thrown in some additional textbook problems that I think you should focus on, but beyond that, today is really just a review. So let's start off with the first question. And this is the reaction of an alkyl halide with ethoxide. That sodium is a spectator ion and the ethanol is just the solvent. This is a common pairing. When you have a nucleophile like ethoxide that also is a strong base, it is common to pair that strong nucleophile, strong base, with its own conjugate acid. That way, if your nucleophile, the ethoxide, misbehaves and goes and starts ripping hydrogens off of things, the most likely substance that it will tear a hydrogen off is its own conjugate acid. And if ethoxide pulls a hydrogen off of ethanol, then you turn your ethoxide into ethanol and turn your ethanol into ethoxide. So it doesn't allow the concentration of your nucleophile to change if you solvate that nucleophile in its own conjugate acid. And for all of the alkoxide bases, like hydroxide or methoxide or ethoxide, this is a pretty common practice. Now, in order to predict the reactivity of this reaction and figure out what the product is going to be, we need to consider the options that are available to ethoxide and alkyl halides. Ethoxide is a strong base, so it's got an ethyl group out here and an oxygen, and it is also a strong nucleophile. So that means that it has a tendency to plug directly into an electrophilic carbon, which is exactly what you expect when you have something like butyl bromide, which this question is asking about. That last one got weird. So here we go. This ethoxide down here is attracted to the partial positive of the carbon right here. And it needs to hit that carbon directly in the backside of the bromide leaving group. And so I'm going to position the molecule up here, and I'm going to throw the electron pair into that carbon right there. Now, this is a primary alkyl halide. And anytime you have an alkyl halide and you are attacking it with an alkoxide nucleophile, like hydroxide or methoxide or ethoxide, you have a tendency for the reaction to go either Sn2, which is what I've shown right here, where you're seeing a substitution, the alkyl halide gets bumped off, and we're going to end up with this as our product. Okay? So this is one potential route of chemistry, and this particular route of chemistry is the Sn2 route. The other route, anytime you have Sn2, there's always going to be a competition with E2. So this carbon right here that the halogen is directly connected to has a neighboring carbon with two hydrogens on it. I should spread those out just a little bit more, but that'll work. For the sake of kind of organizing what's going on here, I'm going to go ahead and color these two hydrogens and show the E2 pathway in red. So these two hydrogens are always there. The ethoxide can come and avoid them and attack this carbon from the backside, or if the ethoxide is positioned incorrectly, and we'll color this one red right here to show that we're looking at a different pathway, and it tries to loop somehow over and hit that carbon right there, the same carbon, what can happen is on its way to that carbon, it will instead come and grab one of these hydrogens. This competition between elimination and substitution is always going to occur when you have E2 versus Sn2 react. Anytime you have Sn2, there's always going to be some chance for an E2 reaction to occur. So I'll color the Sn2 pathway here in blue, And I'll color the E2 pathway in red, and we'll make a note of that, Sn2. And we'll color that, I want to do the whole thing in blue. And then the other pathway that I'm showing in competition with it is this E2 pathway right here. So E2 is always going to be in competition with Sn2. You can't have one without some of the other also occurring. So your job is to predict which pathway is more likely. And it's not that hard. What happens is you just have to focus on what was the nature of the original alkyl halide. So in this case, it was a primary alkyl halide. And for primary alkyl halides, we expect the Sn2 pathway to dominate and the E2 pathway to represent a minor product. So this over here, for primary alkyl halides, we see Sn2 is expected to be greater than E2. And that allows us to predict what's going on in this reaction. Put in my appropriate superscripts, and we have the lesson. So this right here is definitely more detail than the question was originally asking for. It was just asking you to predict the major product. Hopefully this explanation gives you a little bit more understanding of what's going on there. So let's edit this document like that. We'll drop that molecule into that box, close it out. So again, the take-home lesson for this first question wasn't just coming up with an answer. That's not actually that useful. It was understanding why this is the answer, and that why has to do with the constant competition that exists between Sn2 and E2 chemistry. For primary alkyl halides, Sn2 is the major pathway, so we see the ethoxide just come in here and bump off the bromide, and we end up with an ether. The next question illustrates some different concepts. One of those concepts is stereochemistry. So instead of giving us the product, instead of giving us the starting material, it gives us the reagent and the product. And cyanide is one of those strong nucleophiles that you need to recognize. And all of those nucleophiles are listed in question 6.1. So let's take a minute and find that question and talk about it. All right, here's a snippet from your online textbook. This is the Carey, I forget which edition we're looking at. But question 6.1 right here asks you to run, that's table 6.1. Let's find question 6.1. Here we go. So here is, you're asking to react methyl bromide with each of the following compounds. And each of these compounds right here represent common nucleophiles that you need to be familiar with. And so we ignore the spectator ion in all cases. That's a sodium or a potassium or even a lithium. Those are all group 1 alkali metals that don't do any additional chemistry besides allow us to put the nucleophile in a box and ship it to the laboratory. Once it hits the solvent, then we ignore any additional chemistry that alkali metal ion might actually do. And so these different nucleophiles all have a few things in common. First of all, and there's another table of them right here, and this just kind of shows generically, instead of trying to pair them specifically with sodium, lithium, or potassium, it's just telling you that you need some type of metal in order to box these up and ship them to the lab. Once they hit the solvent, then the only thing we care about is the actual nucleophile. The bottom 1, 2, 3, 4, and then the one additional nucleophile that's included in question 6.1 are the various halide ions like chloride, bromide, and iodide. We don't care so much about fluoride because it's a poor nucleophile. So these 4 plus the halide ions represent nucleophiles that are not really basic. And so when we think about the chemistry of a nucleophile, if it's a strong nucleophile, like all of these are, then it tends to go Sn2. The Sn2 versus E2 competition starts to become a problem if your nucleophile is also a base. And that specifically applies to the hydroxide and the alkoxide bases up here. So if we're using one of these other nucleophiles, we just focus on the Sn2. When we use alkoxides and hydroxides, we have to focus on the E2 as well. So now we can come back to this question, and what we're seeing here is that we're starting off with some type of starting material, and we're adding sodium cyanide to it. Cyanide is a strong nucleophile that does not have a lot of base character. So it's pretty much just straight Sn2. And it's going to react with something and bump that something off of this secondary carbon position and produce a cyanide. And so the starting material for this reaction is going to have, and we can choose any starting material we want. So we're going to start off with all of the cyclopentane ring with the methyl group off the side. And then I need some type of group coming off here that is a good leaving group. Alkyl halides tend to be some of our favorite leaving groups, and of the halogens, bromine is generally your favorite. But the truth is here that it would also work if this was a chloride or an iodide or the fat cousin of the alkyl halides, the various tosylates. And you might have noticed that this OTS is a specific type of tosylate, and it looks like this. This is what that particular tosylate looks like, and that's because it's such a beast to draw. That's why we have a tendency just to show it as that OTS. I think on one of the last homework assignments, I gave you a slight variation of OTS where it was the same sulfur dioxide. Oh, whoops. I messed that up. I missed the important part of the tosylate, and that's this component where you have the sulfur right here. So there's a sulfur, and then that sulfur is connected to the benzene ring with the methyl group hanging off of the benzene ring. And on the homework the other night, one of the chalkboard problems, I gave you all of this, only instead of giving you the whole benzene ring, I just gave you this structure. And that's an equivalent tosylate. It's not OTS, it's just a different type of tosylate. And it does the same chemistry. It's a good leaving group. And so as far as your starting material for this reaction goes, you can use any one of the halogens or you can use OTS. So let's try OTS. And I lied. When I said any one of the halogens, we really don't like to use fluorine because it's such a poor leaving group. So any one of the heavier halogens like chlorine, bromine, or iodine, or this OTS. Now, the answer is still not correct because we've ignored the stereochemistry. Notice how this cyanide is currently going away from you. The cyanide was put on the molecule as a result of an Sn2 reaction, and Sn2 chemistry occurs with inversion of stereochemistry, meaning that in order to assure that the cyanide ends up going away from me, I need to start off with a starting material where the leaving group is coming towards me. And when the cyanide comes along and does the Sn2 attack, on the backside it inverts the stereocenter. So this right here is the answer to letter B. Is one of the answers to letter B. Again, you could have used a bromine, a chlorine, or an iodide there and been equally correct. Okay, for the next one. 1-chloro-3-methyl-butane. Well, we need a structure for that. So this is what 1-chloro-3-methyl-butane looks like. This is a little bit of nomenclature practice. We're going to react this with sodium iodide in acetone. Acetone is a common solvent for Sn2 reactions because it is a polar but aprotic solution. And that has to do with the structure of acetone. Remember that aprotics, whoops, I think I hit the wrong keystrokes. There we go. This is acetone right here. Something that is aprotic does not mean that it doesn't have any hydrogens, because acetone certainly does, but the hydrogens in acetone cannot participate in hydrogen bonds. That's what makes acetone an aprotic solvent. And the acetone's job is to solvate both the 1-chloro-3-methylbutane and the sodium iodide, but you want the sodium iodide to be held loosely by your solvent. And so go ahead and put the iodide ion right here. We want the acetone to pull the sodium iodide crystal, because that is just like a table salt, just a little crystal of sodium iodide. You want it to pull it apart into individual ions, but not hang on to it, or else the iodide will never be able to participate in the backside attack. So this is just a pretty straightforward Sn2 reaction. We'll put the lone pairs here and then show the mechanism, which the question doesn't ask for, but you should always be able to show the mechanism for the relatively simple reactions that we're looking at so far this semester. So the iodide comes down, it bumps off the chloride, and anytime you have a mechanism, you want to show all your lone pairs, and we end up with our final product, is just a simple or a halogen substitution, where the chloride becomes an iodide. The letter I is weird in these fonts because it's so small compared to every other halogen symbol. The question you might ask is, well, is there any E2 chemistry? Because if it's Sn2, which is there's got to be some E2 competition. And the answer is there's some, but not even enough to worry about. This is a primary alkyl halide, so Sn2 is already favored. And then iodide is really a weak base. And so it can't do E2. It doesn't have the base strength to accomplish the E2 chemistry. So going back, the question is just asking us to do this. This is all we need in our answer. Next question. Azide. Azide, once again, is one of those nucleophiles that showed up in your textbook right here, metal azide. And the azide is a good nucleophile and a poor base. And when it's a good nucleophile, then it favors substitution chemistry. And when it's a poor base, then we don't expect to see a lot of elimination chemistry. So mechanistically, we don't really care about the sodium. Again, it's a spectator ion. The azide ion has this structure. And it is an ugly ion in terms of formal charges. And also actually a little bit explosive in the laboratory. Azide's often used by microbiologists as an antimicrobial agent. You use it, just a small concentration of azide will kill off a lot of the bacteria. And I'm not sure what the mechanism of bactericide is on that. I anticipate that it's somehow the bacteria try to metabolize the azide and then end up running into some problems. So I always think about this as a double-headed throwing axe. Can't get those ions to be happy. Well, close enough. That it's actually either one of these two external nitrogens ends up being the nucleophilic nitrogen. And so we're going to take this nitrogen on the left-hand side and we're going to plug it directly into that carbon right there. We'll just turn that just a tad. Well, this is never going to be pretty. There we go. And this is an Sn2 attack. Secondary alkyl halides have a tendency to undergo Sn2 chemistry if you attack them with a nucleophile that is not a good base. So we expect to see Sn2 chemistry right here, which means we bounce that bromide off and your final product looks just like your initial starting material, only instead of a bromine on there, we now have that azide. And the azide is just such a pain to draw that it's just commonly abbreviated as N3. And this answer right here is still incorrect. And the reason that the answer is incorrect is because we just saw an Sn2 attack, and Sn2 attacks should cause an inversion of stereochemistry. And so it used to be that there was a hydrogen poking down off of that electrophilic carbon and a bromine that was generally up. And when we see the nucleophilic attack, then the hydrogen gets pushed to the up position and the new nucleophile comes into the down position. As far as making sure that I have the right chair conformation, that tert-butyl group will hang out in the equatorial position all day, every day, all the time. There's even some discussion that a tert-butyl group, because of its strong preference to not be axial and to be in the equatorial position right here, is actually a conformational lock and prevents the chair from actually doing any ring flipping at all. In any event, this is what, whoops, we cut off a little too much. This is what we expect our product to be, and the key point of this question was to get you to think meaningfully about azide, and also to think about the stereochemical inversion that is common when you have an Sn2 reaction. Notice that this is the second time where we've seen a secondary alkyl halide, or in this case a secondary alkyl tosylate, undergo direct Sn2 attack in the presence of a strong base to produce a stereochemically inverted product. And that's the rule. For a secondary alkyl halide, you expect them to undergo an Sn2 reaction. This is a secondary alkyl halide. We're going to react it with another one of the nucleophiles from the textbook. This right here is hydrogen sulfide, is the nucleophile your textbook shows you, and hopefully at this point you're fairly comfortable with the idea that hydrogen and methyl groups, which is what we have right here, are somewhat interchangeable in terms of their chemistry, and it really doesn't affect too much the nucleophilic ability or nucleophilicity of that sulfide ion right there. And so we can show another mechanism for this, although that's not what the question is asking for. Let me redraw this because we want to show the sodium not being there. So we have a methyl group off to the side and a sulfur right here. Once that sodium breaks off as a spectator ion, then the sulfur takes on a net -1 charge and has 3 lone pairs. One of those lone pairs is going to be the reactive nucleophile and will come over here and participate in the backside attack on the electrophilic carbon that bumps off the bromide as a leaving group. And so this is the mechanism of that Sn2 reaction, and your final product will replace, so let's get rid of that lone pair, and we're going to replace the bromine right here for methyl thiolate. So this is our final product, but it's incorrect. As currently written, this final product is wrong, and hopefully you recognize the problem, and it has to do with the stereochemistry. Whenever you have an Sn2, you're going to invert the stereocenter, and so we end up with this as our final product. And we can actually show the stereochemical labels right here, and we should verify that it started off as S, and when we're done, it should be R. Bingo. Oops. Oh, we have more detail in this answer than the question actually calls for. So let me strip that down just a bit. It didn't actually ask us to show the mechanism, and so we just needed to fill in the box with the product. And unless if you're not showing the mechanism, you technically don't need to show your lone pairs. The lone pairs are only required when you're showing the mechanism. So this is the minimum correct answer for this question. Although for the sake of your own notes, I hope that you wrote down and didn't go through the process of erasing the mechanism like I just did in the answer key. All right, last one of these questions. And this particular question, I took these out of your solutions manual. I don't like the way your textbook has set up this question because I think it's a poor question the way that they've worded it. And the reason that it's a poor question is you actually have 2 leaving groups attached to your starting material right here. So your carbon compound has 2 leaving groups on it. Let's make that box a little different sized. This bromide is a leaving group and the fluoride is a leaving group. Between the two, the bromide is certainly a much better leaving group. And so we expect for this nucleophile to come into, these are both secondary alkyl halides, we expect this nucleophile to come in and bounce off the bromide as a leaving group much, much, much faster. Right? It's really easy to bounce a bromide off compared to a fluoride. And so this would be one of the ways of thinking about my product, and it's incorrect. The reason that it's incorrect is because when we do an Sn2 attack, we need to flip the stereocenter. And in a Fisher projection, that's just a left-right flipping. And so this is how your textbook has the question set up. And the reason I don't like this is because given enough time and a high enough concentration of this sodium hydrogen sulfide, it will also bounce the fluoride off. And if it doesn't say how much sodium hydrogen sulfide that you add, then the default assumption of organic chemists is that we add in excess anything that's inorganic, because we can buy that and it's easy and generally cheap. And so you flood the system with sodium hydrogen sulfide. And so we would expect, under the conditions of excess sodium hydrogen sulfide, for it to replace the bromide, and then some minutes or hours afterwards, it would finally go through and finish replacing the fluorides. So I think that this is a much better answer. Your textbook has just the bromide being replaced, and that would only be the case. I would only ask the question and expect you to come up with only the bromide being replaced if I specifically told you that there was only one equivalent of sodium sulfide. So if we change the question to read one equivalent of sodium hydrogen sulfide, not sodium sulfide, sodium hydrogen sulfide, then I would expect you to produce an answer where you only replaced the better leaving group and left the worse leaving group untouched. But if it doesn't specify, then the assumption is excess, so we would expect both of these halogens to be replaced. And the bromide would be replaced much, much faster than the fluoride. All right, let's think about what the whole point of those first exercises was. And there's several things that hopefully you gathered from those in terms of E2 versus Sn2 and inversion of stereocenters and basic reactivity of nucleophiles. But we need to try to organize those into discrete units of memorization. So let's think about a table that we're going to start to produce that looks at alkyl halides. So similar to the alcohol table, which I call the DUI table, this is the alkyl halide table. And remember that tosylates act like just big alkyl halides. But for the sake of simplicity, let's not build that into our title, and we'll just refer to this as alkyl halides. And primary alkyl halides and methyl alkyl halides also have identical reactivity, or at least close enough that we're going to treat them identically. So for the sake of simplicity, we're just going to show this as the alkyl halide table with primary, secondary, and tertiary alkyl halides. In the examples that we looked at so far, what we saw was in the case of a strong nucleophile, which is what all of these examples looked at, was a strong nucleophile reacting with a variety of different alkyl halides. This is an example of a primary alkyl halide, and we reacted it with a strong nucleophile, and the reaction went Sn2. This strong nucleophile also happened to be a strong base. And so when the strong nucleophile can either be a strong nucleophile and a strong base, or a strong nucleophile and a weak base. And the strong nucleophile strong bases are almost exclusively the alkoxide bases: hydroxide, methoxide, ethoxide, and later on we're going to see tert butoxide has kind of some special chemistry. But for now, we're just going to take our world strong nucleophile and divide it up into strong base and weak base. And when it's a primary alkyl halide in the presence of a strong nucleophile that is also a strong base, we saw that Sn2 was greater than E2. But there was still some E2 chemistry that was competing with the Sn2 chemistry. And this is a table that you would have generated in the last lesson, but the table in the last lesson specifically looked at hydroxide. So we're just going to make that more generic and just say in general, if it's a strong nucleophile and a strong base, we expect Sn2 chemistry to be dominant over E2 chemistry. And that's what hopefully we learned from this question right here. This is a secondary alkyl halide, and we reacted it with cyanide. Cyanide is a strong nucleophile because it's out of your textbook. It's this list of 1, 2, 3, 4, 5, 6, and when you include the halogens, the 7. There are 7 strong nucleophiles, but cyanide is a weak base. And in the case of a strong nucleophile weak base like cyanide, then it's essentially just Sn2 chemistry. If there is any E2 chemistry, then it's going to be pretty inconsequential. So it's kind of this deal where Sn2 is much, much, much greater than E2 at the point where we just kind of think, well, that's just Sn2 at that point. Okay? And that was not primary, but secondary. Sorry, the example we looked at. This was a secondary alkyl halide, or specifically an alkyl tosylate. We reacted it with sodium cyanide. It went Sn2. Here is a primary alkyl halide. In this example, we reacted it with iodide, which is a strong nucleophile, but a weak base. And it also went Sn2. Definitely can't go Sn1 because that would result in the formation of a primary carbocation, which is out. So we're kind of fleshing out this table right here based on the examples we've looked at. This was a secondary alkyl halide. We reacted it with sodium azide. Sodium azide is a strong nucleophile weak base with a secondary alkyl halide, so that went Sn2. Nothing new on that question. Secondary alkyl halide with sodium methylthiolate. This is a strong nucleophile and also a weak base, so it is D and E don't teach us anything really different, and both of them illustrate that inversion of stereochemistry that's associated with an Sn2 reaction. And then finally, our last example was 2 different secondary alkyl halides reacted with sodium hydrogen sulfide. This is a strong nucleophile weak base. So yet another example. So basically that question just ran through a bunch of examples of secondary alkyl halides reacting with strong nucleophile weak bases. We kind of can fill in the rest of the chart based on trends we've already seen, and we'll see if we see some examples of these later. When you have a strong base, strong nucleophile like alkoxide or ethoxide, we start to see E2 chemistry dominate over Sn2 chemistry. When you get to the secondary position, and this again is based on subscript. Sorry, I'm trying to talk and manipulate font at the same time. This is based on that hydroxide table that we saw in the last lesson. And then finally, when you get to the tertiary position, Sn2 chemistry becomes nearly impossible for tertiary alkyl halides because there is so much steric hindrance that occurs on the back side. Now, so if you can't have any Sn2 and a weak base is too weak to do E2 chemistry, then we're going to start to see some Sn1 chemistry when it's a strong nucleophile weak base. And I don't have good examples of these three right here. This one, and this one really haven't shown up very meaningfully so far in today's lesson. But I'm going to copy this table and just kind of dump it here at the end of question number 1 so that we kind of appreciate what it is that all of these questions are really trying to teach you as you're looking at what the kind of the examples the book is giving you. All right, this next question asks, how do we make this? This is an ether, contains an oxygen, single bound to 2 different carbons right here. And the short answer of how you make an ether is an Sn2 reaction between an alkoxide and an alkyl halide. Now remember, an ether is made via an Sn2 reaction between an alkoxide and an alkyl halide. Well, let's consult this table that we just made. The Sn2 is the favored pathway between a strong nucleophile and a strong base only when your alkyl halide is primary. So alkoxides are definitely strong bases. And we can't really explore this route over here because we're going to make that ether with an alkoxide, and alkoxides are not weak bases. So in this question that we're looking at right here, if we're going to make an ether, it's going to be a strong base alkoxide. And the only way we can get that Sn2 reaction to work is to have a primary alkyl halide. So really the question becomes, what alkoxide reacted with what primary alkyl halide will give me this compound right here? So we're going to use a technique called retrosynthetic analysis. And in retrosynthetic analysis, we take our product, this is what we're trying to build, and we figure out, well, what can I make that from? And so you kind of clip your product apart. So I'm going to use this line right here. And let's say that I'm going to make this product from, and I'm going to clip this bond retrosynthetically. And I'll show you what that means here. A retrosynthetic arrow also has a different shape to it. Notice the kind of the double-tailed deal. That's specifically a retrosynthetic arrow. And I've tried to avoid using this arrow in examples in the past because it has special meaning to an organic chemist. When you see a compound and then this type of arrow and then some other compound down here, the arrow reads like this. I can make this compound from these compounds down here. So if I try to retrosynthetically clip this bond, basically I'm reverse engineering my starting material. And I'm saying that I'm going to build this. Let me move these out of the way. I'm going to build this ether from these 2 compounds right here. This alkoxide and this alkyl halide. But we need this not to be an alcohol, but rather an alkoxide. Okay? So retrosynthetically speaking is where we take the final product that we know that we want and we think, what can I make that from? That's what that arrow communicates. And if I try to make it from these pieces right here, this is a strong base and a strong nucleophile, and this is a secondary alkyl halide. And if we look at our table, a strong base, strong nucleophile with a secondary alkyl halide will go E2 and more than it will Sn2. So this combination right here is more likely to result in elimination, meaning that that alkoxide oxygen is more likely to come over here and pluck off the hydrogen off of the side and form an alkene instead of hitting that carbon because the carbon right here is secondary. So if this is not a good scheme, then let's come up with another scheme. And for this scheme, I'm going to think about undoing this bond right here. And so we'll color code this to represent the other retrosynthetic scheme. So this scheme right here is kind of a failure. It won't, if you try to put these 2 together, you're unlikely to produce a good yield of this compound because you're more likely to produce an alkene. Instead, if I try to break it apart around that bond, so I'm going to copy and paste this whole structure down over here, but I'm going to clip apart this bond right there, and then I'll make this my alkoxide, and I'll make this my alkyl halide. So what I'm doing right here is I'm saying, can I make this from these pieces right here? And the answer is yes. This is an alkoxide. This is the isopropoxide ion. It is a strong base, strong nucleophile, and I'm reacting it with a primary alkyl halide. On our table, a strong base, strong nucleophile like isopropoxide reacted with a primary alkyl halide will prefer the Sn2 route, which is what we need in order to get that ether. So let's make sure I read the question. Choose the best pair of reactants to form the following ether by an Sn2 reaction. And all of these notes are not required for your correct answer, but hopefully you see kind of how all the pieces fit together. This is how I make ethers up here. And so thinking of this as a generic scheme, then there are two different ways of building this compound from an from an alkoxide and an alkyl halide. And this scheme right here works because it mixes an alkoxide with a primary alkyl halide, which is what you need when you're trying to build an ether. So we just really need these pieces right here. Retrosynthetically speaking, whoops, this is kind of lagging a little bit. That's not great, but that'll work. These are the pieces that I'm going to build this thing from. Okay, that's it for number 2. Number 2 was simply just a review of how do I apply this table when I'm thinking about making something. And if this is the ether that we want, then we have to consider the different possible combinations of strong base, strong nucleophiles and alkyl halides. And we find that there's only one way to get that Sn2 to form the ether that we want, and that's when you have a primary alkyl halide. All right, question number 3, outline the chemical steps necessary to convert. And I'm actually going to go down to B first because it's a little easier. I have these as a single image file. And so notice that this is what I'm starting with right here, and this is what I'm trying to produce. And so notice how the stereo center has switched. This over here is, go ahead and let's attach the stereochemistry. This is an S stereo center, and so this is an R stereo center, which means I should be able to make this thing by direct nucleophilic attack. So the first thing I'm going to do is add sodium methyl thiolate. This is one of the common nucleophiles that hopefully you're starting to recognize from your textbook. These ones right here. The textbook identifies hydrogen sulfides, but if you replace that hydrogen with an alkyl group, it has the same basic chemical features. And so since sodium is simply a spectator ion, really the way to think about this is you have this negative charge and lone pairs that surround that sulfur. And we can try unsuccessfully to just run a simple Sn2 reaction. Why unsuccessfully? Well, let's get rid of that right there. And then we'll try pushing these things together. The reason that this is an unsuccessful reaction has to do with... ChemDraw just crashed on me. The reason that this is an unsuccessful chemical reaction is because hydroxide is a notoriously poor leaving group. It just doesn't come off. So instead, we need to turn this alcohol into a better leaving group. And the way we do that is we tosylate it. So we're just going to take this thing right here. Instead of doing this in one step, which we can't get away with because the methyl thiolate won't push off an OH group, the first thing we have to do is tosylate that. So I'm going to use TSCl, and I'll use pyridine as my catalytic base / solvent. If you remember the mechanism, hopefully that's important to you, and that will end up tosylating the alcohol. When you tosylate this, it doesn't affect the carbon, and the carbon is the thing that's chiral. So that means that we have not done any chemistry at all to this chiral carbon down here, and the tosylation only occurs out here on the oxygen. So no stereochemistry was manipulated in the making of that product. And so then in the second step of this reaction, and you have to do this in 2 separate pots, they call this. You actually have to add in the TSCl and the pyridine in a laboratory, produce your product, and then you purify it, and then you re-add that to your sodium methyl thiolate. And the solvent for this, the second step is an Sn2 reaction. So I want to use a polar aprotic solvent like acetone, or the more common polar aprotic solvent that we use is DMSO. So right here, this illustrates the 2 steps that I would need. The first step is to prepare the alcohol as a leaving group by turning it into essentially an alkyl halide, and then we react the alkyl halide with a strong nucleophile weak base. Let's see if that auto updates in any meaningful way. Oh, there it did. Okay, so I tosylated my alcohol, and now this secondary alkyl halide mimic reacts with a strong nucleophile that's also a weak base, so we expect Sn2 chemistry. Strong nucleophile, weak base, Sn2 chemistry with a secondary alkyl halide. Okay, now we're ready to think about the first one. Now, where'd it go? Shoot. Well, let's try that again. All right, we crashed our computer, evidently, so we're back. So what we want to do now is convert this first compound into the second compound. And you look at that and think, wow, that thing's all ready to go. That is already a secondary alkyl halide mimic. You can react that with sodium cyanide, which is a a strong nucleophile, weak base. So going back once more to our table, a sodium cyanide is a strong nucleophile, weak base. It will react with a secondary alkyl halide or alkyl tosylate in an Sn2 fashion. And it seems like we could just add sodium cyanide to this and it would work, except for the stereochemistry would be wrong. So if we just tried to add sodium cyanide right here, then the product of the sodium cyanide addition would be, instead, you'd end up with the cyanide over here on this. This isn't working either. The cyanide would be over here on the left-hand side and the hydrogen would be on the right-hand side. So that wouldn't work. So that won't work. So what would work? Well, instead, what would work is if you first took off the tosylate and temporarily replaced it with some other leaving group. So I'll have the methyl group up here and the ethyl group on the bottom, and then I'm just going to put, so if I react this with, let's say, sodium bromide, the bromide ion will bump off the tosylate in an Sn2 fashion, and the bromide will end up over here, and that will cause the inversion of the stereocenter. So in the first step, we can add sodium bromide. And since this is an Sn2 reaction, we'll use DMSO as our solvent, a nice polar aprotic solvent. And then in the second step, I'm going to use, I'll use the sodium cyanide, and again in DMSO, and now the cyanide will come over here and bump off the bromide and invert the stereochemistry back kind of the way that it came. So you accomplish this whole reaction in two distinct steps. The first step is sodium bromide / DMSO, and the second step is sodium cyanide / DMSO. And rather than show both of those steps and their intermediates separately, it is common for chemists to just do this. They just put it over the arrow and they number them in the order that you added them in. And so we can take this and dump it back into our document. Oh, except for it didn't save that part. Oh well, I'll fix that in a minute. There we go. Okay, so the next one that we're going to look at is hydrolysis of 3-chloro-2,2-dimethyl-butane. Well, we need to figure out what that thing looks like. 3-chloro-2,2-dimethyl-butane. So we're going to bring this over here into ChemDraw, and we're going to let ChemDraw do the nomenclature work for us. Although you won't have ChemDraw on the exam, so hopefully you're aware of how that's done. If not, let's review it briefly. That we choose the butane as the longest continuous stretch of carbons, 1, 2, 3, 4. At the 2 position, I have 2 methyl groups, and at the 3 position, I have a chlorine. Hydrolysis is a type of solvolysis, and it goes with the same mechanism as what an alcohol would do under the reaction of an alcohol with a halogenic acid. So if you have a secondary alcohol and you're reacting it with hydrochloric acid, it doesn't actually work fast enough. So we're going to pretend that it's hydrobromic acid, and the mechanism would be Sn1 with a shift. So we expect a secondary alcohol to react with a halogenic acid via an Sn1 mechanism with the potential for a carbocation shift. If that's what we expect for the alcohol, then for the solvolysis reaction, we expect the alkyl halide to do the same thing. An Sn1 mechanism means that in the first step of the mechanism, the chloride falls off. We end up producing a carbocation intermediate. So I'll the carbocation right here. And then we have to watch out for the shift. Just because it says an asterisk, it doesn't mean that there has to be a shift. It means there could be a shift. And in this particular case, you expect a shift to occur when either a hydride or a methyl can walk over a position, and we can end up with a better carbocation. Notice that the arrow that I drew comes from the middle of the bond and not from either end. That's how you show a shift occurring. And that shift is going to end up producing a compound that looks like this. And the carbocation is now at this position. Now, you should ask yourself, did I make a better carbocation? And the answer is yes, definitely you did. You went from a secondary carbocation here to a tertiary, so we expect that shift to occur. In the next step of the mechanism, and we're already way past the rate determining step because that was the first step, the next step of the mechanism is where water comes in as a nucleophile and captures that carbocation. And I believe that's correct because the question said hydrolysis. Hydrolysis is specific to, it's the Solvolysis reaction specifically involving water. So we know water is present because of the word hydrolysis. And that water is going to come over here and stick to that carbocation. That'll work right there. Now instead of a carbocation at this position, I have a water stuck to this thing. There's our water. One lone pair, formal charge of +1, and 2 hydrogens out here on the end. And then something's got to pull one of these hydrogens off of the water to get our final product. So our final product is going to look like this without an extra hydrogen on that water. Okay? So let me just kind of get ready to draw that thing. And now we have to ask, okay, what would do that? So in order for this chemical reaction to occur, some base is going to need to come along and pull one of these 2 hydrogens off. Water is certainly the best base in this particular reaction to accomplish that, but there is a chloride ion floating along somewhere in solution, and so it's not wrong. It's weird, but it's not wrong to show the chloride ion pulling off that hydrogen. We just don't expect the chloride ion to do that because it's just not that good at it. Okay, so here's the full mechanism for this reaction. Explain this observation using the mechanism. And that's it's funny when you ask an organic chemist a question, a lot of times we just answer it by drawing out the mechanism. And then if you ask what does that mean, then they point emphatically at the mechanism and expect you to figure that out. So this is, they told us what the product was. It's 2,3-dimethyl 2-butanol. This is 1,2,3,4. So this is a butane with an alcohol right there, so butanol. The alcohol is at the 2 position, as is a methyl group, meaning the other methyl group is at the 3 position. So this is the correct compound that this question is asking you to show a mechanism to justify. The purpose of this question was to illustrate that concept of carbocation shifts while also reviewing the mechanism for solvolysis in general. Solvolysis does not fit nicely on this table that we came up with right here. And the reason for that is that water is not a strong nucleophile. And so we're going to have to look at, we're going to add in some weak nucleophile columns to this table later on. And, well, we may as well. We'll tack on solvolysis here as the other reaction, solvolysis. And the solvolysis for a primary alkyl halide. Remember in solvolysis, the key thing is that the halogen has to fall off. But you can't fall, a halogen can't fall off the primary position because that would go Sn1. And you can't have a carbocation there. So instead, it's got to go Sn2. You won't see Sn1 reactions occurring on primary anything because that would result in the formation of a primary carbocation. And primary carbocations are forbidden, expressly forbidden in a general organic chemistry class. Secondary alkyl halides, though, have no problem with Sn1 reactions for solvolysis, and the same is true for tertiary. So this is where we see a big difference. Solvolysis involves a weak nucleophile. The weak nucleophile has to wait for the carbocation. A strong nucleophile doesn't have to wait for the carbocation. It pushes the leaving group directly off and skips the carbocation entirely. So this table right here brings in the mechanisms of solvolysis in kind of one little organized unit. So I'll go ahead and update that. Okay, next question. It says identify the class of reactions as Sn1 or Sn2. Oops. It bugs me not to have these N's properly subscripted. And write the kinetic equation for the solvolysis of tert butyl bromide in methanol. So solvolysis means that the solvent is replacing the halogen, and tert butyl bromide is a tertiary alkyl halide. So going back up to our table, when you have a tertiary alkyl halide and a solvolysis reaction, tertiary alkyl halide solvolysis, that means it's going to go Sn1. So just based on the table, we know that this reaction will go Sn1. So the question asks, write the kinetic, identify the class of reaction, that's part one. Write the kinetic, so the rate is equal to some rate constant times the concentration of the only thing that's involved in the rate determining step. Well, we'll have to come back and look at that once we come up with a mechanism. And then we also want the chemical equation, and we'll show that with Lewis structures. So let's go back over to ChemDraw to answer the rest of this question. We want the solvolysis of tert butyl bromide. So I'm going to go ahead and just turn this thing right here into tert butyl bromide with a few edits. And then we can get rid of everything else that we're not going to need right here. So this right here is now tert butyl bromide. And in the solvolysis reaction of a tertiary alkyl halide, we expect for the first step to be the rate determining step. This is the formation of the carbocation intermediate, and based on our table, we expect this to be an Sn1 mechanism, which means we have a carbocation formed. And so our first carbocation intermediate will look like this. Let's put the carbocation in there. And then the solvent is going to come and plug into that carbocation in this next step. We don't expect a shift to occur because it's already a tertiary carbocation. The solvent that we're using is methanol in this reaction, so I need to bring in a molecule of methanol. Methanol is also a weak nucleophile, so this is not a good description of that table that we drew until we added in the solvolysis step. So here is the mechanistic detail right there, and then we're going to have this doesn't necessarily involve any type of inversion of stereocenter. Whoops, I'm going to flip this vertically and put the methanol down here. We have an oxygen right here, but that oxygen is connected to a methanol, and there's also still that hydrogen off the methanol is still connected to it. And so our last step will require us to remove that hydrogen off of that position. And just like we can use water as a catalytic base to do that, we can also use methanol as a catalytic base. It's the solvent, so it's everywhere. So that methanol will come over here and pull the hydrogen off. Or if you want, you can actually show a bromide doing that. It's just bromide's not very good at doing that. So our final product will be this compound right here. We went from tert butyl chloride to a tert butyl, and it's essentially a methoxide. It's an ether at that point. The chemical, this is the mechanism, and that's not what the question was asking for. It was just asking for you to show the chemical equation. So the chemical equation would start off with your starting material, typical reagent like methanol. We can just take here and put over the top of the arrow. You could just write that out as MEOH if you want, and then we put our final product. So there's our chemical reaction. All right, so, and then finally the kinetic. Well, let's look at that rate determining step. In the rate determining step, the only thing that's involved is the tert butyl bromide. So that means that the rate of this chemical reaction is equal to some rate constant times the concentration of tert butyl bromide. Sn1 means that the kinetics are first order. First order kinetics means that the rate of the chemical reaction is a function of the concentration of only one thing. So here's all parts of that question answered. Now it's asking for the reaction of chlorocyclohexane with sodium azide. Let's draw that out to see what it looks like. We're going to show it mechanistically. We want chlorocyclohexane. So there's my cyclohexane. And there's chlorine. I don't like that last lone pair. And we're going to react this with sodium azide. Hopefully you appreciate how little we care about sodium at this point. So I'm just going to draw out the azide ion in its Lewis structure glory. So you got two lone pairs on each end. And then we have positive formal charge on the center nitrogen and negative formal charges on these external nitrogens right there. Okay, let's go ahead and use our table to try to predict what's going on with this reaction. In our table, it tells us that if we have a secondary alkyl halide, which is exactly what we have, that's a secondary alkyl halide because the halogen is attached to a carbon that's connected to two other carbons. That secondary alkyl halide will react with a strong nucleophile, which is exactly what azide is. Azide is a strong nucleophile and a weak base. The only strong nucleophile strong bases that you need to worry about are the alkoxide ones, the metal hydroxide, the metal alkoxide, hydroxide, methoxide, ethoxide, etc. The rest of those that we're going to see on this chart out of your book are all weak bases. And so if it is a strong nucleophile weak base and it's a secondary alkyl halide, then we expect the chemistry to be Sn2. Sn2 chemistry means that in a single step, this azide will circle, and the arrow here doesn't really kind of do justice to the nature of the backside attack. Technically, I would need the azide to come in and hit this thing directly at that carbon. We're not actually that picky about the directionality of our arrows. As long as you've connected the right atom to the right carbon, then you're okay. And I don't like that I kind of missed it. There, that feels better. All right, this is concerted in one step. The azide comes on there and displaces that chlorine. There would be inversion of stereochemistry if this was a chiral center, and it's not. Going off of this carbon on both directions is the exact same ring system, so it does not meet the criteria of being a chiral center. And here's my final product. If we don't, the question is going to ask us to show the chemical equation, which is all of this, just without the mechanism. So this is the chemistry of what I just did right here, and you're welcome to leave in the mechanism if you want. Most of these lessons are kind of for your own notes anyway. All right, so we have now the chemical reaction. We also want to talk about what type of mechanism this is, and so this is Sn2, based on me correctly applying that table that we used above, and therefore if it's Sn2, that means the kinetics are second order, and the rate is going to be equal to the constant, rate is equal to rate constant times the concentration of two things. The first thing would be the chlorocyclohexane, and the second thing is going to be the azide. We'll go ahead and call it sodium azide or azide if you want. It really doesn't matter. The chemist knows that it's just the azide that's doing all the chemistry right here. So it's kind of a weird question to ask you to show the rate law, but if you know it's Sn1, then the rate law involves just a single compound. If it's Sn2, then the rate law should involve two separate compounds. That's what that question is getting at. Okay, next question. Provide a brief explanation of why the halogen exchange reaction shown is an acceptable synthetic method. We have an isopropyl bromide. We're reacting that with sodium iodide to get isopropyl iodide and sodium bromide. To think about what that looks like in terms of structures, here is my isopropyl bromide. That's what the question started off with. And I'm going to react that with sodium iodide. And the solvent for this reaction will be acetone. And the product of this reaction is going to end up being isopropyl iodide. They ask, why can this happen? Well, this is a pretty straightforward Sn2 reaction. secondary alkyl halide in the presence of a strong nucleophile that is a weak base. Let's go back and look at that on the table. Secondary alkyl halide in the presence of a strong nucleophile that is a weak base will go Sn2. But the question really is asking is, why does the reaction work? Because you'll notice that one of the products you're going to build up in the course of this reaction is sodium bromide. And so when the iodide bounces off the bromide in an Sn2 backside attack, you're going to end up with some amount of bromide present. And why doesn't the bromide just come along and bounce off the iodide and push the reaction to the reverse equilibrium? There's two reasons for that. One is, well, you just put a lot of sodium iodide in there. You dump in a ton of sodium iodide. That's a reactant. And when you flood the system with reactant, Le Chatelier's principle tells you that it's going to go towards the product. There's also kind of a special little detail here that I don't think anybody should be required to memorize at this level of your education. But acetone can dissolve sodium iodide. It does not dissolve sodium bromide, which means that when you start producing sodium bromide as a product in this reaction, it immediately precipitates out of the solution and cannot participate in the reverse reaction because it's locked up as a salt, a crystal on the bottom of your container. So because of the lack of solubility of sodium bromide in acetone, this reaction definitely goes 100% or so, like 99.9 to completion, and the sodium bromide really can't escape the crystal lattice to turn the chemistry around. And so that's kind of a detailed answer that I don't think students need to know all the solubility rules of every compound in every organic solvent. So instead, we're just going to refer to this as the answer is why. So Le Chatelier's principle allows us to flood the system with NaI and drive equilibrium to products. That's kind of the most useful answer to this question. Oh shoot. And Le Chatelier's was somebody's name, so it deserves a capitalization, I guess. There's also like a special little accent mark or some kind of upside down V that goes over the I, I think, or the E. I can't remember, but doesn't matter. Briefly explain why the reaction of 1-bromobutane with sodium azide occurs faster in dimethyl sulfoxide than in water. Well, let's go back to our table. 1-bromobutane is a primary alkyl halide. Azide is a weak base, strong nucleophile. So 1-bromobutane is a primary alkyl halide. Azide is a weak base, strong nucleophile. So that means that this reaction goes via an Sn2 mechanism. So briefly, primary alkyl halides react with weak base, strong nucleophiles via Sn2 reactions. Sn2 reactions occur faster in aprotic solvents such as DMSO because the protic solvents bind the nucleophile too tightly. What does that mean? Let's go back and think about this reaction right here. The iodide needs to attack that carbon and bump off the bromide in the only step of the mechanism. So because it's the only step, that means it's the rate determining step. Your solvent needs to be able to dissolve sodium iodide, which acetone can do, but it needs to do it very gently. Water will also dissolve sodium iodide, but when it does that, the water forms a complex shell around the iodide and actually prevents the iodide from doing any other chemistry. Water is a protic solvent, and it dissolves your nucleophile too well and gums it up. So we want for an Sn2 reaction, we want to make sure that we use a polar aprotic solvent. All right, number 8. Write chemical structures for compounds A through D in the following reaction sequence. Compounds A and C are alcohols. So what's going on here? Well, somebody took a compound, reacted it with sodium amide to get something else, and then they took a different compound, reacted it with hydrobromic acid to get something else, and then they took both of those something else's and they combined them together to get this ether right here. This is really a nice question, and it ties together a lot of concepts. So the first thing we want to think about is, well, how do you get an ether? And the answer to that, so far in your world of chemistry, the only way that you really know how to make an ether is by combining an alkoxide together with an alkyl halide. So that should tell you that compounds B and D, one of these is an alkoxide, and one of them is an alkyl halide. And I already circled it. B ends up being your alkoxide, and D ends up being your alkyl halide. D is actually a little easier to figure out because we're going to take hydrobromic acid and heat up something in the presence of hydrobromic acid and end up with an alkyl halide. And that makes sense. When you have an alcohol and you heat it up in the presence of hydrobromic acid, you end up with an alkyl bromide. The other one, sodium amide, is above all a base. And to make an alkoxide, you have to rip a hydrogen off of an alcohol. So we're going to take some alcohol, we're going to rip its hydrogen off, and we're going to end up with that alkoxide. So those are kind of how we're getting the pieces. Now, just like we did before, when we were looking at this ether, we have to ask retrosynthetically, what are the two different ways I can make this ether? I can either make it by forming this last bond here, or I can make it by forming that bond over there. Let's color the one on the left-hand side red, and we'll color the one on the right-hand side blue. And then we'll use our retrosynthetic arrows to ask the question, what can I make this compound up here from? And so if we take these pieces, here and here, and then I'm going to cut this bond. The blue bond right here means I'm cutting that thing, and the red bond means I'm cutting that thing. And we combine these. Remember, we have to make them by taking an alkoxide and reacting it with some type of alkyl halide. I'll call that an X. And for this one over here, there would be an X right there. Let's fix the structure a little bit and then spread this thing out. Okay, so that means that if I take the blue, this is the bond that I'm kind of unmaking when I'm reverse engineering my product, I could make this compound from these two pieces, or I could make the same compound from these two pieces over here. This is a primary alkyl halide with an alkoxide base. This is a tertiary alkyl halide with an alkoxide base. Going back to our table, alkoxide bases are strong nucleophile, strong base. I need an Sn2 reaction, which means that if my alkyl halide is secondary or tertiary, I will get E2 primarily. So that means that this is a tertiary alkyl halide. This alkoxide base is actually going to do E2 chemistry and produce an alkene, not Sn2 chemistry to make the ether. So these are the pieces that I need to combine in order to get this compound. So that means that one of these is B and one of these is D, and then this is the final product that I'm going to make out of this reaction. Okay? So we're going to combine this compound with this compound, an alkoxide with a primary alkyl halide to get my ether. The B right here, this compound that has a bromine has to be made by adding hydrobromic acid. And this compound up here that is deprotonated is going to be deprotonated using sodium amide. All sodium amide does is start off with some alcohol and rip its hydrogen off. So sodium amide is going to take this alcohol, that strong base will rip the hydrogen off, and we'll end up with this alkoxide. This alkoxide combines with this alkyl halide to form this ether over here. What alcohol would I need in order to make this? Well, hydrobromic acid reacts with primary, secondary, and tertiary alcohols to produce alkyl bromides. So I'm going to start off here with ethanol, and then this compound that I'm start off with here is methyl cyclohexanol. Okay. So now we're ready to identify compound A, B, C, and D. So we'll make a little spot here for A, for B, for C, and for D. And A is this alcohol right here. I don't need the name anymore, but why not? B is going to be the ethanol right there. Ooh, this got a little messy. Let's spread these out just a tad. There's A, and here's B, and then C and D. So whoops, I did that wrong. C was this one, and D was the alkyl bromide equivalent of this one, and then B was this alkoxide. I don't have you learn names of ions very often, so I'm about to be surprised to see what ChemDraw calls this thing. 1-methyl cyclohexanol-1-olate. Oh, that's interesting. No one cares. Okay, so we'll take these compounds, and this answers the question of what is A, what is B, and what is C, and what is D. Write a mechanism describing the solvolysis, Sn1, of 1-bromo-1-methyl cyclohexane in ethanol. Now, we've already done quite a few Sn1 solvolysis reactions. Let's go find one. Where did I put that one? Oh, here's an Sn1 solvolysis reaction. So we're going to start with this as kind of a template and just apply our understanding of Sn1 solvolysis to a new example that they're giving us. All right, the starting material that we're supposed to use here is 1-bromo-1-methyl cyclohexane. Oops, I need to grab that and move it up here. And that compound looks like, oops, this right here. Okay, so 1-bromo-1-methyl cyclohexane in a solvolysis reaction. Make sure we have the solvent. Oh, in ethanol. So it's not going to involve water. So this compound I have here is not super helpful. Well, let's just start from scratch. So this bromine right here in the first step of an Sn1 solvolysis is going to fall off. And I really don't know that I needed to tell you that this is Sn1. From the table that we had before, the solvolysis reaction of a tertiary alkyl halide is going to be Sn1. And so when that thing falls off, then we end up with our tertiary carbocation. Because the carbocation is tertiary, then we do not expect a shift to occur because life doesn't get any better. Normally we like to bring water in here in this next step, but because the solvent was specifically identified as ethanol, this solvolysis would be called an ethanolysis reaction. So instead of water plugging in this step, we're going to have ethanol plug in this step. And we're going to have almost to our final product. Let's see. This is now an oxygen. We've got an extra hydrogen and an ethyl group hanging off of this thing. So there's my ethyl group, and there's my hydrogen, and there's my positive charge. I'll slide this methyl group a little bit out of the way and then crunch things down so I can stay on my page. Okay, in the final step, we're all done now as soon as we take that hydrogen off. So we're actually going to use another molecule of ethanol to come over there and take that hydrogen off, and we'll be done. I feel like we've seen a bunch of these. Not sure that this question added anything new. Perhaps just a peer review of concepts that we've already seen. And we'll put the lone pair back on again. And we're done. A nice 3-step Sn1 with no shift. Solvolysis, okay, of the compound below. Occurs with carbocation rearrangement. Well, this is a secondary alkyl halide, and we're undergoing solvolysis in the presence of water. So let's check to make sure that our table shows that. Oh, hey, now it does. So a secondary alkyl halide in solvolysis will go Sn1 with the potential for a shift. And so the question is now asking us to show a mechanism. So we'll grab this, take it over to ChemDraw, and spit out yet another Sn1 mechanism. I did not intend for this to take all this time. Hopefully this has been helpful to you as a review and just kind of bring together some of the various concepts that we've gone through. If nothing else, you get to watch me tool around forever in ChemDraw, making lots of happy little mistakes. All right, so this secondary carbocation is adjacent to a carbon. That hydrogen's been there the whole time. Anytime you have a secondary carbocation, you should expect a shift, especially when the question specifically identifies that there is a shift, which is the case in this question. That kind of level of kindness and mercy is not something that I typically show students on an exam. I expect you guys to know when a carbocation shift will occur because you'll have seen so very many of them by this point. in the next step. This is solvolysis using water. So we need to bring a water in. I'm going to steal my water from up here. And we'll bring that water and plug it into the carbocation. It is common, and I think bad form, to plug your lone pair into the positive charge. So I usually try to plug it right at the atom and not at the positive charge, but I've seen people that'll do that. And an even greater offense is when they don't ever show their lone pairs and instead just drag the arrow from a negative charge. And that's pretty lazy. So make sure to show your lone pairs. All right, we don't need to show this hydrogen anymore because its role is already kind of done. The water plugged into this position, and now we've got to remove one of the two hydrogens coming off that water in the final step. Over and over again, I've told you that when you pull that last hydrogen off, then you can use a water. It's the most likely thing, but certainly there are some bromide ions present that could also pull that off. I'm going to use a water because that's the highest probability scenario. Let's go ahead and trim our water down just a tad. We don't need all of those bonds. And we grab that hydrogen, and then the electrons need to drop from the bond over to the oxygen. And that lone pair is kind of in the way, so I'm going to move it over. And now we're down to our final product. Okay, there's another Sn1 hydrolysis mechanism. 1, 2, 3, 4 steps. 3 steps is the normal. 4 steps is what occurs when you have some type of hydride shift or methyl shift. Right, the structure. Did we see a methyl shift on this one? I thought we did. Yeah, right here. One of the things that students sometimes forget about is that you do expect shifts to occur when it's either a hydride or a methyl group. In question number 4, we saw the methyl shift. If it's a competition between a hydride and a methyl, you expect the hydride to shift first. So anyway, those are the answers to this one. Need to work through these problems. I don't have any new things for you to define. And that will conclude the section for chapter 6. And now you're ready to take exam number 2, which typically covers chapters 4, 5, and 6.